Good afternoon. I welcome you all to this lecture session of the course Laws of Thermodynamics. Now today we will come to a very important topic, that is the concept of entropy in the perspective of classical thermodynamics through its definition by heat transfer in a reversible process. Okay. So, if we do this now, entropy, its concept in the perspective of classical thermodynamics through its definition of heat transfer in a reversible process, how it is done. Now, we have already learned if there is a heat engine, reversible heat engine operating between a source T1, a reversible heat engine operating between a source T1 and a sink T2. This T1 and T2 are in absolute thermodynamic scale of temperature, taking heat Q1, rejecting heat Q2. We know that Q1 by T1, or rather Q1 by Q2, first I write T1 by T2. This can be written as Q1 by T1 is equal to Q2 by T2. This can be written as Q1 by T1 plus minus Q2 by T2 equals to 0. What is this? With respect to the heat engine, that it is the cyclic integral, the integration in a cyclic process of del Q. This is the reversible engine, R by T. Cyclic integral, this is the cyclic integral, del Q R by T. For a simple formula, concept comes Q1 by T1, Q1 is the heat added, Q2 is the heat rejected, this is a minus sign, that means algebraic sum of Q by T in a cyclic process for a reversible heat engine is 0. This is a great concept. This you can also prove in a general reversible cycle, engine operating on a reversible cycle which does not take heat at a constant temperature. The source is also not at a constant temperature, because if the system goes on constant, not at constant temperature, I have already told that the surroundings, that the body from where it will take heat, reservoir or source, that will also vary in its temperature. That also I have discussed earlier. Similarly, for T2, in this case you can derive the same equation. This is a very simple case, we derived it, the concept, sole concept is derived. Let us consider in a thermodynamic plane PV a closed loop like that, which is in general represents a cycle. Now in this case we can divide this cycle, thermodynamic cycle, into infinite small elemental Carnot cycles, infinite number of elemental Carnot cycle like this. If we have number of reversible adiabatic, if we divide this like this, all are reversible adiabatics, and by reversible isothermal process. As you know, the Carnot cycle consists of reversible isothermal processes and reversible adiabatic processes. Similarly here, the low temperature region, we can divide like this. That means we can divide this cycle into number of elemental Carnot cycle, so that though the temperature is varying, we consider for any elemental cycle, for example this, the temperature is T1 and heat added is delta Q1. For this elemental cycle, the heat added is delta Q1 dash at a temperature T1 dash. For this elemental cycle, the heat added, the elemental heat added is delta Q1 double dash and the temperature is T1 double dash. So now for the small elemental portion of this process, temperature remains constant. That means when we divided the cycle into elemental Carnot cycle, then we can consider the temperature remains constant where a small amount of heat is added. Like that, in this case heat rejection also we can consider delta Q2 at a temperature T2 for this elemental cycle, delta Q2 dash at a temperature T2 dash for this elemental cycle, delta Q2 double dash at T2 double dash, and so on. It is very simple, just an extension of this, and for each elemental cycle we can write delta Q1 by T1 is delta Q2 by T2, simply this. Similarly, delta Q1 dash by T1 dash is delta Q2 dash by T2 dash, and delta Q1 double dash T1 double dash for all this, delta Q2 double dash T2 double dash, and so on. So that if we add this, we get sigma delta Q1 by T1 is sigma delta Q2 by T2, delta Q2 by T2. So therefore, by adding this we get sigma delta Q1 by T1 is equal to sigma delta Q2 by T2, which means sigma delta Q1 by T1 minus delta Q2 by T2 over a cycle is equal to 0. And minus Q2 because of the heat rejection, if you take like within this, that means it is algebraic sum of delta Q by T over this cycle, which can be written as cyclic integral delta Q by T, delta Q by T is 0. And here all heat transfer is reversible. I am not writing the suffix reversible, actually final expression I write the reversible. So delta QR by T is 0. So therefore, from this simple logical proof we get that for a reversible heat engine or for a reversible thermodynamic cycle, delta QR by T equals to 0. Now in this case I will, okay, I can rub this one. So now I can rub this one. Now, and a very important concept is that this delta QR for a cycle, delta QT now if the cycle is reversible, totally reversible. Now reversibility is of two types, internally reversible and externally reversible, I tell you. Now what about this temperature? Is it the temperature of the source or the thermal reservoir, surrounding thermal reservoir, or the temperature of the heat engine? Now the question comes, if the heat transfer is not reversible, there may be a temperature difference. But if heat transfer is the reversible process, then the temperature difference will not be there, whether it will be a source temperature or the temperature of the working system while receiving heat is same. And similarly, whether it is sink temperature or temperature of the working system during heat rejection, doesn't matter, they are same. But this may not be the case. Then the question comes, how we will tell the heat engine as a reversible heat engine? If the heat transfer process is not reversible, it takes under a finite temperature difference. In this context, there are two things which is very important for you to know. One is internal irreversibility, which I discussed earlier also, internal irreversibility, and external irreversibility. External irreversibility. Now, internal irreversibility of any process due to the internal dissipative effects like mechanical friction, mechanical hysteresis, fluid viscosity, inelasticity, all these things, electrical resistance. But external irreversibility we conceive as the irreversibility due to the heat transfer through a finite temperature difference. That means if you consider one as a system, another as the surrounding, so surrounding and system has a temperature difference. So therefore, a heat engine may be internally reversible, that means there is no dissipation internally due to all these things, friction, hysteresis, magnetic hysteresis, fluid viscosity, all these things, but it may take heat under a finite temperature difference where it will be externally irreversible. That means if cycle has to be totally reversible, it has to be both internally reversible and externally reversible. That means irreversibility both externally and internally to be 0. That means there is no friction within the system, there is no internal irreversibility, and at the same time the heat transfer will take place across a infinite small temperature difference. Okay, so this is the case. This is the case for a simple single process also. For example, I tell you, this is very important concept, that if a mass of gas expands in a piston cylinder arrangement, the piston goes out because of its pressure, and also it takes heat from a surrounding temperature TH, for example, hot body. The gas temperature is such at any time, the gas temperature at any instant of the process is always less than TH, so that the finite amount of heat goes to the gas. You understand? So therefore, you see this heat transfer, the TH and the system boundary heat transfer, the system boundary temperature or the system temperature, if it passes through equilibrium states, then is finite, because of which heat is transferred. Now consider a process that this process is infinitely slow, free from any internal irreversibility, no friction, nothing. But the heat is transferred from a high temperature source to the gas where there is a finite temperature difference. The process has external irreversibility but internally reversible. Externally irreversible, internally reversible. But if the heat transfer takes place from a temperature which is always at the same temperature or infinite small difference with the gas temperature, if gas temperature varies accordingly, this outside temperature will vary, so that always there will be an infinite small temperature difference, then it is externally reversible. And at the same time it is free from internal dissipation, internally reversible, it is totally reversible. Now with the similar concept, when a cycle operates with internally reversible but externally irreversible, that means a cycle which is internally reversible, internally reversible, internally reversible, internally reversible, but externally irreversible, but externally irreversible. That means it takes heat from source or sink which has a different temperature than the temperature of the working system, which receives heat or rejects heat. In that cycle is known as endo reversible. That means which is internally reversible. This is a very useful concept, endo reversible cycle. And for a heat engine operating in an endo reversible cycle, then the cyclic integral del Q R by T is again 0, where this reversible means the endo reversible process, and this T is the temperature of the working system during heat transfer process, not that of the reservoirs. But if the cycle is totally reversible, not endo reversible, then this temperature of the system and the temperature of the source or sink remains the same. Okay? So now with this we will proceed further. Therefore, you consider an endo reversible cycle, and we will see, and we will call this as a reversible cycle. We are not bothered much about the external irreversibility, so that del Q R by T cyclic integral is 0. Now this gives a beautiful idea that when some change over the cycle is 0, then what happens? If you define now del Q R by T as we can define exact differential of a point function S. Why? Because if you substitute this, then del Q R by T is ds, it has to be 0. So whenever, if we substitute ds, let us consider change of any parameter S. If we differential change, then if we substitute this, we see cyclic integral is 0. The cyclic integral of any parameter is 0 means this is a point function, and this becomes a property of the system. The way you read earlier, we discussed that in first law del q minus del w, its cyclic integral is 0, and that is why del q minus del w, if it is replaced by d of a exact a point function d of e, the cyclic integral d of e is 0, because point function the cyclic integral is 0, and that way the definition of internal energy came up. Okay. So, similarly here also you see, in that case we have found, now I write for a first law, we show that we found that del q minus del w in a cyclic process is 0. So, if you substitute this as d of a parameter e is 0, that means E is a state function, point function, whatever you call. Though they too are path function, their difference is a point function. This was discussed in first law. Similarly, though q is a point function, but delta qr by t, that becomes path function. Q is a path function, delta qr by t becomes a point function. So, this S is known as entropy. So, therefore, by definition the entropy is this, ds is del qr by t, or a finite change in entropy in a process is del qr by t. Del qr by t. Okay. Now see that this way the birth of entropy, or the first definition of entropy, comes like this through its change. A differential change is del qr by t, and a finite change del qr by t. That means for process connecting two states 1 to 2, S2 minus S1 is this quantity, del qr by t integral 1 to 2. And this S is a point function, entropy is as a property, because it satisfies this relation cyclic integral ds equals to 0. That is why the del q by r by t enjoys the characteristic that it can be expressed in terms of the exact differential of a point function, which is the property entropy. That means del q r by t from one state point to other state point is independent of the path, because it is a property, it is a point function, so it is independent of the path. That is the most vital thing. That means if we have two state points 1 and 2, and if they are connected by number of reversible process, let us consider 1, A2, all are reversible process. Okay? B1, it is a reversible process, RA, this is RB, this is RC from state 1 to 2. The value of this will be same, which means that integral del q r by t through 1 RA2, that means this path, equals to del q r by t 1 RB2 and equals to del q r by t 1 RC2. That means whichever path we follow, if it connects 2 points, then this integral is point function. Obviously, this is defined like that. This is del S, S2 minus S1. So, S2 minus S1 is fixed. Entropy at 2 is fixed, the state point. So, this is the point function, S1 is fixed. So, whatever way we go, the change in V, just like the work done in a conservative force field. So, that whatever path we take, the change of entropy is given by this integral, and this integral is irrespective of the path. That means, if we connect 2 points by any reversible path, then the value of del qr by t, that reversible path will give the change of entropy of the in the process, by the system of the system in the process. Now, the big question comes, what happens if the process is an irreversible one? Now, for an irreversible process, now for an irreversible cycle which is internally irreversible, whether it is externally reversible or not, it does not matter if the cycle is internally irreversible. And you can consider is externally also irreversible. Is internally irreversible, it is the irreversible cycle. Here T is the system temperature. So, that is why I am bothered with internal reversibility. Is irreversible cycle del cyclic integral del q by t is not equal to 0, because cyclic integral del q by t we have proved equals to 0 provided the cycle is reversible. So, in case of irreversible cycle, whether this temperature is the source or sink temperature or this temperature of the working system, the cyclic integral never equals to 0. Now, the question comes, what is this value of cyclic integral del q by t in an irreversible process as compared to cyclic integral del q by t in a reversible process, or integral del q by t in a single process with compared to its counterpart in a reversible process. Now, this question comes into picture, that what is its value. Now, one thing, since del q by t not is equal to 0, this is true that integral del q by t is a path function, not a point function. So, two questions come. First question, what is the value of del q by t in an irreversible process? Now, if we have an irreversible process, let us consider an irreversible process 1A2. I am doing it by dotted line. The first question is there, if we have if a system executes an irreversible process from 1 to 2, and if I evaluate integral del q by t 1A2, would it give it delta s? No, because delta s by definition is del q r t 1 to 2 by any reversible process. That means we have to connect this by a reversible process, which means you can tell verbally that the entropy change in a irreversible process connecting two states equal to integral of del q by t, this value, if the states could have been connected by a reversible process, and then what could have been the value of del q by t in that reversible process is its entropy change, not del q by t through its own process. So, therefore, next question comes, then what is the value of del q by t for this irreversible path compared to its counterpart del q r by t in a reversible path? And similarly, for this cyclic integral, what is the value as compared to this? This is 0. This is 0. And now I write that this thing you can better understand. This is the process B, that if we have a number of irreversible path, del q by t for each path A, B, C are not equal. That means it is not equal to the integral of del q by t 1 B 2, not equal to del q by t 1 C 2, not equal. They are not path functions. But the entropy change will be delta s by any reversible process connecting the two states S2 minus S1 is given by delta QR 1 RA2 or 1 any reversible process, because they are same. That means delta QR by T by any reversible process is same, because they are the point function, they define the entropy change. While irreversible processes, delta Q by T is not the entropy change. It is simply delta Q by T integral over the process, and these are different for different irreversible process. Now again I am telling, question comes how it is compared with their counterpart. This question was answered by Clausius and is known as Clausius inequality. Okay. Now this was answered by Clausius and is known as Clausius inequality. Very simple proof, its concept. I tell you the result, that cyclic integral del q by t for a irreversible process is less than del q by t for a reversible process. You consider Endo reversible, so that T is the temperature of the working system. Since this is 0, so cyclic integral del q by T is less than 0. This is Clausius inequality in terms of cyclic integral, and hence it follows that delta q by T in any process, for example 1 to 2, is less than its 1 to 2 in a reversible process. That means this is less than, this is by definition S2 minus S1, or we can tell del q by T finite value is less than the del S in terms of finite changes. So therefore, this in this form and this cyclic integral del q by t is less than its counterpart cyclic integral in reversible cycle, that means less than 0. Similarly, integral del q by t over a given process is less than this counterpart, that means integral del q by r by t over that process, which is nothing but change of entropy delta S. So, this gives you the concept of, it gives you the Clausius statement, the answer done by what is very simple to prove. The proof lies in this: efficiency of an irreversible engine is less than that of a reversible engine. That's simple like that. That means a reversible engine, if you consider a irreversible engine T2, take Q1, irreversible heat engine, and same temperature T2. Let us consider the engine is totally reversible. Then Q1 by T1 is equal to Q2 by T2. Or simply you can write, rather this is better way, Q1 by Q2 is Q1 by Q2, it is irreversible engine, we cannot write this, sorry. Now you consider an irreversible engine, its efficiency eta is 1 minus, by definition of first law, that is from conservation of energy. We know the eta, the thermal efficiency is 1 minus Q2 by Q1. Q1 minus Q2 is work divided by the heat. Now if we have a reversible heat engine between the same source T1, this is T1, same source and sink temperature, then efficiency is defined as, and in that case if Q2R and Q1R is the heat rejection and heat received by the heat engine, that becomes is equal to 1 minus T2 by T1. This is for a reversible engine. So since eta less than eta reversible, that means 1 minus Q2 by Q1 is less than 1 minus T2 by T1. That means Q2 by Q1 is greater than T2 by T1, and again we can write Q1 by Q2 is less than T1 by T2, which gives Q1 by T1 minus Q2 by T2 equals to 0. So you see the proof that simple, the concept, pivotal concept is that irreversible engine efficiency is less than the reversible. T1, T2 source sink temperature, irreversible engine, the efficiency is defined like that from the conservation of energy. We know it, earlier discussed. For a reversible engine is also defined like that, where Q2 or Q1 are the quantities Q2, Q1 heat rejected, heat added for a reversible engine. But for a reversible engine I can replace this by T2 by T1. But since eta is less than eta by Carnot's principle, 1 minus Q2 by Q1 is less. That means Q1 by Q2 is less, that means Q1, that means Q2 by Q1 is higher than T2 by T1, or Q1 by Q2 is less than T1 by T2. Q1 by Q2 is less than, that means Q1 by T1 is less than Q2 by T2, so that Q1 by T1 minus Q2 by T2 less than 0, not equal to less than 0. That means the cyclic integral del Q by T is less. Again you can prove it by taking a general loop as a thermodynamic cycle for irreversible cycle and compare it with the reversible one, you get the same result. So this is for your logical proof, I do it. So the information is like this. This is very important information from fundamental concept point of view, that Clausius inequality tells that delta Q by T cyclic integral is less than 0, the counterpart, and in counterpart in reversible process, and delta Q by T over a given process is less than its counterpart delta Q by R by T in the reversible process, that is equal to delta S. Now with this concept we write that this one we can write in a different way. This one we can write in a different way, that for an irreversible process now we can write this way. You just now let us consider an irreversible process which is internally irreversible. For an irreversible process, delta S is Rather, I can write in differential term, ds is greater than del q by t for that irreversible process from the Clausius inequality. Del q by t is less than del s, or del s is greater than del qr by t in the process. That means the change of entropy, that means the corresponding part delta q by t in a reversible process is always greater than that in a irreversible process, the differential form. In a finite difference form, the change in entropy in a process is always greater than delta qr by t. Clear? Now, if I write for an irreversible process, delta s is always, sorry, not reversible, delta s greater than del q by t, is del q by t. Since delta s is greater than the integral del q by t for that irreversible process, we can write this plus some positive quantity which I write as delta si, which I write as delta si, which is always greater than 0, because delta s of any process is more than delta q by t, that process over that process, this integral plus delta si, and delta si is greater than 0. This can be written in differential form, ds is delta q by t plus dsi, where dsi in differential form is greater than 0, and this is known as entropy change due to internal irreversibility. This is known as entropy change due to internal irreversibility, as I have described earlier, due to internal irreversibility, due to internal irreversibility, and which is always greater than 0. Entropy change due to internal irreversibility is always greater than 0. So, this is one very important relation in classical irreversible thermodynamics. The delta s in a process, change in entropy, is delta q by t integral plus delta si. Now, you consider certain special case. For example, for special case is reversible heat transfer process. That means a heat transfer process with, but the process is reversible, then delta si will be 0, then delta si will be 0, and the result will be delta s is integral, which was the basic definition of delta s, that change in entropy. Entropy is always defined from its inception in terms of the change. Delta s is delta qr by t. So, for any reversible process with heat transfer, if delta q, if heat is added to the system, delta s is positive. If heat is taken out from the system, delta s is negative. Now, you consider reversible irreversible heat transfer process. Rather, you consider heat transfer process, irreversible heat transfer process, irreversible heat transfer process, irreversible heat transfer process, irreversible heat transfer process. In that case, delta si is not 0, because irreversible heat transfer is there. That means this resembles the same equation, delta s, delta q by t plus delta si. Now, you consider reversible without heat transfer, that is reversible adiabatic process. These are the special case. Now, in a reversible adiabatic process, this is beautiful. Because of reversible, internally reversible, delta si is 0, delta q is also 0. That means in this case, delta s is 0. That means entropy remains same, doesn't change. And we get, if we have a irreversible process with heat, without heat transfer, that means an adiabatic process. An adiabatic, simple adiabatic. If the word reversible is not added with the adiabatic, simple adiabatic process means irreversible process without heat transfer. Simple adiabatic means natural adiabatic process, natural adiabatic process. If you add reversible, that means reversible adiabatic process, reversible process without heat transfer. This is a process without heat transfer but not reversible. In that case, what will happen? delta q by t is 0. That means delta q by t is 0. So in that case, delta s is equal to delta si. And since delta si is always greater than 0, delta s is greater than 0. Delta si has to be greater than 0 because of the Clausius inequality. So therefore, in an adiabatic process which is irreversible but without heat transfer to the surrounding, the change of entropy is always greater than 0. So these two, this one and this one, is very important, that reversible adiabatic process entropy remains constant, whereas irreversible adiabatic process, the simple adiabatic process, delta S is greater than 0, whereas reversible heat transfer process, delta S is del QR by T. In that case, del Q by T in a reversible process by definition is del S. And for an irreversible heat transfer process, this is the equation. But one very important thing I tell you in this case, that in certain cases, is a very special case if a process is irreversible and loses heat to the surrounding, rejects heat to the surrounding, this is negative. And because of its internal irreversibility, this is positive always, delta Si greater than 0. It may so happen these two may balance each other to give delta is 0. That means the initial entropy is the final entropy. Entropy remains the same. But this is not same as this delta is 0, because here reversible process which passes through the series of equilibrium states. So in a reversible adiabatic process, entropy remains same in the entire process. But here delta is 0, that means the entropy change may be 0, but it may not be that the process is isentropic. This is known as isentropic process. Isentropic. That means at all points, state points of the process, entropy remains same. But here the entropy change may be 0 because of the balance between the two. That means irreversible process rejects it at the same time because of internal irreversibility delta Si, which is positive and negative may make 0. I will solve an interesting problem to explain this. Now, okay, today it is up to this.